Evet, kayda başladım. Şimdi geçen hafta konumuz neydi arkadaşlar? Rotate left, rotate through, carry left, rotate right, rotate through, carry right'lardı. 2 tane örnek yapmıştık. 3. örneği size ödev vermiştim. DX, BX, AX register'ını komple 48 bitlik bir register'ımız gibi düşünüp 4 kere sola rotate eden programı yazmanızı istemiştim. 48 bitlik bir register rotate eden bir komutumuz yoktu. O yüzden bir trik, bir cevap bulmanız gerekiyordu buna. Cevabı bana gönderen arkadaşlarınız oldu. Cevabımız şöyle basit. Cevabın üzerinden gideceğim. Şunu biraz zoom yapayım ama çok kötü görünüyor. Set font'tan bunu 20'ye çıkarayım. Benim fontum yok burada, çok kötü. Tamam. Neyse. Başka bir font seçeyim. Terminal değil. Kusura bakmayın arkadaşlar. Evet. AX, BX, DX'in içerisinde bunlar olsun dedik. Aslında içerisinde olan şey A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. Bunların hepsi hexadesimal şeklinde değerler. İşte DX'in içerisinde bu, BX'in içerisinde bu, AX'in içerisinde bu. Şurası ACBD olmuş. ABCD. Böyle bir 16 çarpı 3 48 bitlik bir register'ımızın olduğunu varsayalım. Bunu rotate etmenizi istemiştim 4 kere. O yüzden bir tane döngü kurulmuş loop içerisinde. Loop dediğimiz şey Cx kaç kere dönmesini belirliyorsa o kadar dönüyordu. Hatırlayın, 4 kere dönecek. Ondan sonra yaptığımız işlem aslında önce a-1 bit sola kaydırıp bunu rotate through carry left ile yapıp bu araya bir tane carry biti atarak, hepsinde bir tane carry atarak, bu arada carry biti atarak bu sayının ya da bu sayının most significant bitini carry bite düşürüp sonrasında ondan sonra gelen olan değişkeni register'ı bx'i rotate through carry left ile yapıp bu ax'ten çıkan carry'yi bx'e sokarak sonrasında bx'ten çıkan carry'yi dx'e sokarak normalde aklımıza gelen ilk cevap bu oluyordu arkadaşlar. Fakat dx'i rotate ettiğimiz zaman bu most significant bit'in, burası karakter bit olması gerekiyor. Bit olarak düşünün. Most significant bit'in AX'e geri girmesi gerekiyor arkadaşlar. Burada yapmanız gereken bir şey var. Önce AX'e rotate ettiğiniz için bunun most significant bitini önce bir dışarı çıkartıp AX'e sokacak hale getirmeniz lazım. Yani şu iki satır rotate left deyip most significant bitini carry'e çıkartıp rotate right deyip dx'i orijinal haline getirdiğiniz zaman carry'de dx'in most significant biti kalıyor. Bu most significant biti de rotate through carry ax dediğiniz zaman ax'e sokuyorsunuz. Emulate deyip görelim. Bu ekranda görünüyor mu tam emin değilim ama. Evet. Şimdi birinci döngü. Birinci döngüden sonra bir bit değiştiği için bir şey anlayamıyoruz. 4'ü tamamlandıktan sonra bakalım. Mesela 4'ü tamamlandıktan sonra dx'in içerisinde b, c, d, e, f1, 2, 3, 4, 5, 6 bakın a. D'nin içerisindeki a, ax'e girdi. Cevabımız buydu. Bu geçen haftanın sorusuyla alakalı sorusu olan var mı? Hızlıca cevaplayabilirim sorusunu. Yoksa yeni derse geçiyorum. Okay, let me switch into English. Let me close this example and open the new PDF. PDF 9, PDF 10, assignment 10. This week we are going to cover the stack architecture. Stack architecture actually push and pop, covers with push and pop commands. We have stack pointer and stack segment. Please remember, in our emulator we have stack pointer and stack segment in here. this stack pointer and stack segment shows us the top of a stack. We have a stack button in here. If you open the stack button in here, you can see the stack values. Actually, this is just a memory location. If I open this memory location by hand, I can see the values in there. These are sorry, should be 100 and FFFE. Why it's not going there? Let me open again. It's not opening. FFFE. Yes. So this is the top of the stack. Stack goes like that. Sorry, stack goes upwards. Top of the stack is here. It goes upwards by decreasing. The important stuff is stack is last in first out. LIFO example. In tutorials parts, we have part 9, the stack part. The stack part explains some concepts. Let me read some of these concepts to you. Stack is an area of memory for keeping temporary data. This part is unnecessary for you. We can use the stack to keep any other data. There are two instructions that work with the stack. Push comment and pop comment. These both commands work with 16-bit values. Just a single parameter. Syntax is push register, push S register, push memory, or push immediate. But push immediate is not supported our 8086 architecture. When we open the instruction set and go to push command, for example, we can clearly see that push immediate works only on 186 CPU and later. 8086 is the previous architecture, so push immediate is not working. But our emulator can understand and work. The push immediate command will work. Just know that. Okay, push command. It has a one parameter, which is register, S register, or memory. It stores a 16-bit value from this parameter into stack. Let me write a simple example. I'm going to put 1173 hash into AX, and I'm going to push AX into stack. Okay, I emulate this, open the stack. Okay, AX says 1173. Push AX means pushing 1173 into stack segment, stack pointer combinations location. This is stack segment, stack pointer pointer. It points to top of the stack. As you can see, this was FFFE. When I run the push command, it becomes FFFC. It decreased by 2 because push commands first update the stack pointer by decreasing it 2 and then copy the value into stack at the top of the stack. Okay, so in here we have the value of FFFE, top of the stack. When we push AX into stack, stacks will be updated, decreased by 2. It becomes FFFC. As you can see, the 1173 is written into FFFC. This is 16-bit value. Every line within this stack pop-up is 16-bit value, but please remember, in our emulator, every line is 8-bit. For example, 8-bit, 8-bit. These two 8-bit copied into 16-bit stack. Actually, let's go over and look at the stack location and see where it is stored. This is stack location, FFFC, FFFD. These two locations showed by a pointer FFFC. Okay, push command is this. After that, I'm going to update AX with 0, and then I'm going to pop value into AX again and see the example again. Okay, we have stack. We change the AX into 1173, push AX into stack, 1173 is into stack. I changed the AX into 0 manually. I manually changed the AX into 0 and then make a pop operation. Pop operation is gathering value from stack. Let's go over and look at the pop operation. Pop is here, exactly same S register or memory, single parameter, get 16-bit value from the stack. Algorithm is start by copying the value from stack and then updating stack pointer by increasing 2. Okay, so it will copy this FFFC location, word FFFC location into AX and increase the stack pointer. Okay, let's see. As you can see, stack pointer with this arrow, this shows the stack pointer, location of the top of the stack. But please be careful. Stack is not emptied out. It still contains our value, but just the pointer is updated. But when I push again a new value, for example, I'm going to push an immediate value. This is actually wrong, but let me push it because our emulator can handle this for me. Okay, I update it. I push 1173 into stack, update AX manually to 0 in order to change the C. See the change. Okay, I pop AX and head of the stack is changed. Now I'm going to push again. It will change FFFC value into 886. As you can see, it's overwrite the previous value of stack because we only know that stack is only full till its top. Okay, these are important concepts. These are the syntax. Push and pop work with 16-bit values only. Push immediate work with only this CPU and laters. Architecture is last in first out architecture, which means, let's say this is a stack, a bottle of glass or whatever you use. The first in will be last out, which is exactly last in first out. For example, when you push 1, 2, 3, 4, 5 and start popping, you will get 5 first because this will pop out first and then this and then this. It goes like that. It is very important to do equal number of push and pops, otherwise the stack may be corrupted and it will be impossible to return the operating system. Be careful, try to do similar number of push and pops. Don't lose within the stack. Return instruction, return within the stack, blah blah. Push and pop instructions are especially useful because we don't have too much registers to operate with. So here's a trick. Please remember, in our emulator we have limited registers: AX, BX, CX, DX, SI, DI, etc. But you can directly use stack as a register and store some values in there and get some values from there. It is unlimited as our memory available. Okay, here's a simple trick. Store original value of the register in stack using push. Use the register for any purpose. Restore the original value of the register from the stack. What it is talking about? It's talking about something. For example, I use AX as a value, BX another value, CX another value, DX another value. I don't want to change this value within our program. I want to use this register as they are, but before, but there isn't any other registers. Before try to define a variable, I push, for example, dx into stacks and update, for example, dx with 73 and make some calculations with dx. After all this operation, let me pop dx. This will revert the original value back, but I have already made my calculations and necessary things, etc. Let me show you this. 1, 2, 3, 4. I push the value into stack. 4 is in the stack, which is dx. Okay, make some calculations. Dx is 73. Increase dx. Dx is 74. Add 2. Dx is 76. And pop dx. Dx will be restored into original value. As you can see, it is 1, 2, 3, 4. This is what it's talking about. Okay. Another use of the stack is exchanging the values. Please remember, when we exchange value, we use the temporary register. For example, ax has the value 5, bx has the value of 6. We want to exchange this value. How it can be done? I can put the ax value into cx and bx value into ax and cx value into ax bx again. This is a simple swap operation. Look at the a and b. These are 5 and 6. I just switch them. They are now 6 and 5. You can use stack. I'm going to push ax and push bx into stacks and then pop ax and pop bx. After this push and pop operation, the order is important. It's first we pushed ax, then bx. The head is now bx, the bottom is ax, but I'm going to pop a value from the top of the stack, which was bx, and I'm copying it into ax value. This way, 5 and 6, we push this value into stack. These are here, 5 and 6. I'm going to pop it into ax, pop it into bx. As you can see, I exchange the value of a and b without using any other register, but just a stack. It gives an example about that. The exchange happens because the stack uses last in first out algorithm. I already covered that. The algorithm is like this. We already covered that. The current address pointed by stack segment stack pointer is called the top of the stack. Please remember this visualization. The top of the stack is here, the above 5. Top of the stack shows the last used location. According to top of the stack, in order to push, we subtract 2 first and update the top of the stack and write the value. While popping, using pop instruction, we copy the value from the top of the stack and then update the stack pointer. These are important things. This is from tutorial. These are from instruction sets. Okay, oops, not close that one. Okay, there are some other push and pops. Let me show you also that. For example, push A. Push A is not for 8086 architecture, it's for 186 architecture. It pushes all general purpose registers AX, CX, DX, BX, SP, BP, SI, DI into stack by a single command without any operands. Okay. For example, AX has the value of 73H. CX has the value of 86. I couldn't write 86, sorry. 886, blah blah. For example, SI has the value of 1. I push all and return. Let me open the stack. Please look at the stack. Before looking at the stack segment is also another segment register and it can be also changed. I'm going to change the stack segment by using AX. Okay, I'm going to change the stack location. For example, it is now 100 and FFFE. Let me change that location, and as you can see, stack is from 200 and FFFE. Okay, AX has 1173, CX has 8086, SI has 1. With a single command, with no operand at all after that, push all command, I'm going to copy all the values within these general purpose registers into stacks. Okay, here is the values. The order is important. Order is ACDB. Stack is like this: ACDB, SPBP-SI, SPBP-SI. Look at the SI value is 1. We copy all the general purpose registers into stack. There are also, you can copy all the copied value into, copy it back into general purpose registers. For example, I'm going to change the source index, change the AX value into 1, decrease CX, and then use pop A. Pop A is exactly opposite version of push A. It gathers the all general purpose registers into registers, from stack to registers. Okay, we put some value in there. Stack is filled with general purpose registers. I have updated source index AX and CX. CX is here, AX is here, source index is here. All these values are updated. Now I'm going to restore the original value that I call push A. When I pop A, as you can see, source index becomes 1, stack pointer becomes FE, AX become 1173, CX become 8086. All the original value is restored. Okay, another push and pop command is push flex and pop flex. Again, please remember that flag register is a 16-bit single register. Every sum of every bit is represents some flags. For example, carry flag is the third flag of the flag register, etc. So a flag register is a single 16-bit value register. You can copy this register into stack with push F command. Let me use push F in here and pop F in here. I'm going to open the flags, open the stack, go to one by one. Okay, within this location, all the flags are 0. Only instruction interrupt enable flag is 1. Push F will be copied 202. Let's change this code into something more meaningful and set carry flag. Move FF, decrease CX, etc. and see the changes now. Okay, here we have carry flag set bit set carry. After some operations, the current value of the flag register is 203 hexadecimal. After some operations, please look at the values. lots of values is changed, but when I use popf, the previous version of the flex will be restored, which is 202, 3. It will restore the original values of the flex into line 6. Okay, this is push F. Okay, pop F, push F, these are opposite versions. We have covered all the topics about stacks. Is there any question? Ahmed, I couldn't catch your question. You should open your microphone and say something because I couldn't read what you write. What do you mean by? Hocam sadece üçüncü değerin pop edilmesini istiyoruz. Bunu yapabilir miyiz? Üçüncü değerden kastın ne? Ahmet aramızda değil sanırım. Anyway, the question. We have a single question. The Turkish version and an English version. Write a program that calculates the first 24 Fibonacci numbers and stores numbers in descending order in memory starting at 208 memory address. Okay, Fibonacci numbers. Who knows the Fibonacci numbers? Let me ask you a simple question. Fibonacci number starts with what? What is the first Fibonacci number? Mohammed says 0. Another guess. Okay, Ahmed. What is the first Fibonacci number, Ahmed? Do you know Fibonacci numbers? Ahmed also says 0. Okay, you have complete consensus. All of the students answer my question, said that Fibonacci numbers start with 0. You are right, as a mathsfun.com, as a Wikipedia, etc. But some of the resources says that Fibonacci numbers start with 1, but some of them says that it starts with 0. Anyway, it's not that important. Let me explain the Fibonacci numbers to you. I'm going to update Sublime later. Okay, the first Fibonacci number, 0. The second Fibonacci numbers, 1. The third Fibonacci number, we will calculate it with addition of the first and the second, which is 1. The fourth Fibonacci number, we will calculate it with the second and third, which is 2. The previous 2 addition is what a Fibonacci number is. Okay, 34, 55 goes like this. I want you to calculate the first 24 Fibonacci numbers. Actually, the question wants us to calculate the first 24 Fibonacci numbers and stores number in descending order. Descending means decreasing order. So the 24th Fibonacci number will be in 2000H address. 23rd Fibonacci number will be in 2002 H address, etc. It goes like that. So what we are going to do? We need to use stack. We need to run loop. Let me write a loop. This loop will run 24 times or something. I'm going to change that if it is necessary. In the first case, I'm going to find and push these Fibonacci numbers into stack one by one. I'm going to use push AX or something. I don't know, push something. After finding and calculating all the Fibonacci numbers, stack is filled with Fibonacci numbers. Then I need another loop. Okay, we have another loop. This loop will also run some CX times. The numbers are not that important for now. Within this loop, I'm going to pop the last Fibonacci number, the 24th Fibonacci number from the stack, and copy it into, for example, AX, and after that, store this value into 2000H memory address, starting from that memory address, and will need to be increased. That's why I can't use an immediate value here. This will always use the 2000 location. I can use source index and increase the source index by 2 at every loop iteration. But we have also Stoss word. Please remember, Stoss words is an instruction which stores X into exasegment destination index couple. So, calling Stoss word without any parameters automatically stores AX into exasegment destination index location. If I update destination index with 2000H, this line will automatically use exasegment destination index and copy the 2000H location. Okay, so the second loop is this. The copying value from stack to memory is easy part. After the second loop, we need to return control to operating system, which needs to be done in proper way. I couldn't remember the proper interrupt of, it was 4C, I remember. I need to 4C into AH and call interrupt 21H. This is return to operating system. Control to operating system. Okay, second loop is done. The first loop, calculating the Fibonacci numbers, the hard part. Okay, as I show you, the first two numbers is already known. That's how I can calculate the later Fibonacci numbers, by adding the last two ones. Remember, so the first two needs to be pushed into stack or put it into registers. For example, AX and BX. These are the first two numbers of Fibonacci. First two Fibonacci numbers. I'm going to directly push this AX and BX into stack, so that my code needs to run only 22 times, because the two Fibonacci numbers is here, the other 22 will be calculated. Okay, we are going to push something. At first, we need to calculate the Fibonacci numbers. This is, sorry, this part is inner version of the loop. These are the inner version of the loop. I try to be visually readable, because these are important things in order you to understand. Okay, I have AX and BX. I need to add these two values in order to calculate the third value. Okay, now the third value is in AX. I need to put this value into something different, like DX, and push the DX into stack. But before pushing DX, or after pushing DX, I need to make swap operation. For example, I need to update AX with BX, BX with DX. Okay, is this true? I have put the DX, the third value into DX, the second value into AX, okay, the third value into BX. Okay, let's see if this is correct or not. By the way, I want to change this text segment. For example, we didn't use CX. I want to change segment into 200. Yep. Okay, we have changed the stack segment into 200. Open the stacks. It doesn't need the flex. Okay, this is stacks. Stack 0 and 1. This value, put it into stack. This is the first Fibonacci. This is the second Fibonacci. Okay, the third Fibonacci is calculated, which is in DX now. DX has the 1. AX is updated with BX. BX is updated with DX. And we push the DX, the third value, into stack. No, this is wrong. Let me see if this is wrong or right. No, it goes correctly. 1, 1, 2, 3, 5, 8, D is 5, 8, 13. D is 13. 13, 14, 15, 16. Yeah, D is 13. Okay, so this is true. Either BX or DX should be pushed into stack. But DX is updated with AX. AX into DX, DX into BX. At the end, it should be BX. Yep. This is the more proper way. 1, 2, 3, 4, 5, etc. goes like that. Let's run this one. Program has returned control to operating system. Let's go over and look at the 200 memory location. Dive into the first ones. Okay. 0, 1, 1, 2, 3, 5, 8, D, 15, 22. Goes like this till 6F F1. 6F F1. Let me Google the 24th Fibonacci number. Okay, 24th Fibonacci number will be 46 converter 16 bits decimal, which is B520. It's not 6FF1. B520. Let me look at the 23rd one. We make some error at some locations. This is 6FF1. Yeah, this is the 23rd Fibonacci number. It didn't calculate the 24th Fibonacci number. Okay, how can we correct this? Stack doesn't have the value, so it doesn't calculate it and pushed into stack. Let me change this into 23. Okay, run this code. 6FF1B520. Yep, This way I can find the 23rd Fibonacci numbers, but I wonder what it says first Fibonacci number. Most probably it will gather the value from the Wikipedia. What are the Fibonacci numbers? First Fibonacci is 0. Anyway, the one is bigger or greater, it's not that important. We have calculated the Fibonacci sequences, put it into stack, and put it back into memory by pop and stoss word codes. Okay. Any question? Any question about stacks? Any question about Fibonacci, pop, push? Okay, let me explain something for you. Next week will be our last week that we make some lessons, because June of 7 will be the starting week of the finals. So the next week will be our last week. In the next week, I'm going to cover the procedures and call operation. We write simple procedures and functions, let's say functions. We use push pop instructions again and call procedures. After that lessons, I want you to ask me any question you have about this lecture, about this lesson, okay? So far I have nothing to tell about. Course is finished. If there isn't any question, I'm stopping this record. Yep, I'm stopping this record.